This is Geography 2104, Lesson 11, Spatial Analysis in Geoprocessing, Section 4. So a quick summary of spatial overlay analysis. Overlays are the combination of spatial and attribute data for two or more spatial layers. In this example, we have attributes from layer A and attributes from layer B, and when they are added together, we have overlay attributes that combine A and B. Polygon overlay. Here the overlays of two layers produce four distinct polygons. The output polygons have attribute properties from both parent layers. This is basically the theory behind the intersect and union tools. So we have 1, 2 polygons, and layer 2 we have another 1 and another 2. And our output layer has attributes from 1, 2, 3, and 4. Both intersect and union tools are examples of overlay tools within ArcMap. The intersect method preserves only those features falling within the spatial extent common to both layers. The features of the input layer are intersected or sliced by the intersect layer. The attribute data from both layers are included in the new layer's attribute table. Union creates a new layer by combining two polygon layers. The new layer has data and shapes from both layers, including their intersection. Point and polygon analysis involve adding to the attribute properties of a point feature based on the polygon in which it resides. What happens when you have multiple points in the same polygon? In spatial join, you can count and summarize. This is basically the theory behind spatial join. Spatial join, the basis of point and polygon. Again, a reminder that spatial join is a type of table join operation in which fields from one layer's attribute table are appended to another layer's attribute table based on the relative locations of the features in the two layers. A quick overview of principles of spatial analysis. We've covered measurements, scope, queries, proximity functions, and geoprocessing. We'll move on to spatial estimation, triangular irregular networks. We've covered these in polygons. Area analysis, including area and shape, and density for point, line, and kernel. Spatial estimation, specifically spatial interpolation. The procedure of estimating the values of properties at unsampled sites within an area covered by existing observations, basically educated guessing at the stuff in between. Spatial input data for these processes are usually stratified sampling or regularly spaced observations, random, unevenly located, patchy, clustered observations at specific locations, usually convenience or access related, and adaptive. This method for estimating feature variation is used to locate sample sites in areas of high variation. The object of spatial interpolation is to fill in the gaps for the areas that we know nothing about. So the idea is, let's say we have A, sample point at A, and we've got a B, sample point at B, a sample point at C. The question is, what's the value at sample point D if we haven't actually sampled there? Interpolation. Estimating the values of properties at unsampled sites within the area covered by existing observations. Interpolation is widely used for climate data and predictive statistics. Data structures should be point files or sample sites and an interval or ratio data structure. Keep in mind Tobler's first law of geography. Data must be spatially autocorrelated. Generally, this only works for continuous variable sampling. Triangular irregular networks. Adjacent data points are connected by lines to form a network of irregular triangles. The value at each data point is known, and the distance between these points can be calculated. Therefore, a linear equation in trigonometry can be used to work out the value for any other point within the boundary of the network. Area analysis, including area calculation and shape. Area is difficult to calculate by hand within a geographic environment. In this sense, trapezia or lines are dropped from each corner to the x-axis, and their areas are calculated, as in a difference in x times an average of y. The trapezia for the first three edges, shown in yellow, orange, and blue, are summed. When the fourth trapezium is formed from the blue arrow, its area is negative because its starting point has a larger x than its endpoint. When this area is subtracted from the total, the result is the correct area of the polygon. In reality, we just use ArcGIS. With this, the process here is add new field, right-click, and calculate geometry. This will be detailed in your last ArcGIS video. Shape. Not something that we've ever looked at, but GIS can be used to characterize shape. Basically, the perimeter relative to the area. How is this calculated? Shape equals the perimeter of your polygon divided by the square root of the area times 3.54. Square root of the area is used so that the area and the perimeter are in the same units. The factor 3.54 is the square root of pi times 2. The application of this factor means that something resembling a circle would receive the value of 1. Very distended or distorted shapes will have a much higher value. Examples of this include gerrymandering and how far districts such as North Carolina District 12 here are far from a circle. Density analysis in ArcMap. Let's look at calculating density surfaces in ArcMap. With density tools, you can calculate the density of input features, typically vectors, within a neighborhood around output raster cells. By calculating density, you are in a sense spreading the values of the input over a surface. The magnitude at each sample location, line or point, is distributed throughout the study area, and a density value is calculated for each cell in the output raster. For density maps, a circular search area is applied that determines the distance to search for sample locations, line or point, or to spread the values out around each location and calculate a density value. For kernel density, it calculates a magnitude per unit area from point or polyline features using a kernel function to fit a smooth, tapered surface to each point or polyline. For line density calculates a magnitude per unit area from a polyline feature that falls within the radius around each output cell. And for point density calculates a magnitude per unit area from point features that fall within a neighborhood around each cell. For point density, in a simple density calculation, points or lines that fall within the search area are summed and then divided by the search area size to get each cell's density value. No tapering off within the search radius as you have with kernel density, which we'll talk about in a second. The point density tool calculates the density of point features around each input raster cell. Conceptually, a neighborhood is defined around each raster cell center, and the number of points that fall within the neighborhood is totaled and divided by the area of the neighborhood. The line density tool calculates the density of linear features in the neighborhood of each output raster cell. Density is calculated in units of length per unit of area. Conceptually, a circle is drawn around each raster cell center using the search radius. The length of the portion of each line that falls within the circle is multiplied by its population field value. These figures are summed, and the total is divided by the circle's area. The figure below illustrates this concept. So what proportion of the search area contains a linear feature? A raster cell in the circular neighborhood used to determine the length of the line density. Here. The illustration above, a raster cell is shown with its circular neighborhood. Lines L1 and L2 represent the length of the portion of each line that falls within the circle. The corresponding population values are V1 and V2. Thus, density equals L1 times V1 plus L2 times V2 divided by the area of the circle. If a population field other than none is used, the length of the line is considered to be its actual length times the values of the population field for that line. Possible uses for line density include finding density of roads as an influence on wildlife habitat, or density of utility lines in a town. A population field can be used to weight some roads or utility lines more heavily than others, depending on their size or class. For example, a divided highway probably has more impact than a narrow dirt road, and a high-tension line has more impact than a standard electrical pole. Again, point density, we have an output grid cell and a search radius. In each point, let's call this point A, would have a value of, let's say, 60, and point B, let's say a value of 35. Within this area, these values are summed and divided by the area. Kernel density analysis. The kernel density tool calculates the density of features in a neighborhood around those features. It can be calculated for both point and line features. Possible uses include finding density of houses, crime reports, or roads or utility lines influencing a town or wildlife habitat. The population field could be used to weight some features more heavily than others, depending on their meaning, or to allow one point to represent several observations. For example, one address might represent a condominium with 6 units, or some crimes might be weighted more heavily than others in determining overall crime levels. Clinic opening hours to determine provider services is another example. So how does kernel density work? Conceptually, a smooth, curved surface is fitted over each point. The surface value is highest at the location of the point and diminishes with increasing distance from the point, reaching 0 at the search radius distance from the point. The density at each input raster cell is calculated by adding the values of all the kernel surfaces where they overlay the raster cell center. It's a little like a series of buffers is initially created for the points, and then the values are redistributed to the raster cells. Within kernel density, only a circular neighborhood is possible. The volume under the surface equals the population value for the point, or 1 if none is specified. If a population field setting other than none is used, each item's value determines the number of times to count the point. For example, a value of 3 would cause the point to be counted as 3 points. The values can be integer or floating point. By default, a unit is selected based on the linear unit of the projection definition of the input feature class data, or as otherwise specified in the output coordinate system environmental settings. If an area unit is selected, the calculated density for the cell is multiplied by the appropriate factor before it is written to an output cell. For example, if the input units are meters, the output area units will default to square kilometers. Comparing a unit scale factor of meters to kilometers will result in values being different by a multiplier of 1 million, or 1,000 meters squared. So conceptually, again, we have the kernel that is in 3 dimensions. Let's say, and up, with diminishing influence farther out to the edge of the boundary. We are calculating a magnet area for point or polylines with this kernel function and fitting its smoothly tapered surface over each point or polyline. The magnitude or process per unit area is total kernel density divided by area unit. The kernel height defaults to 1 and can assign height based on an attribute using the population field parameter. Search radius. You're asking the computer at what distance does this process affect the system of interest. The difference between the two. The difference between point density and line density tools is that the first is applied to point features and the second to linear features. The two calculate the quantity specified by the population field that falls within the identified neighborhood and divide that quantity by the area of the neighborhood. Kernel density spreads the known quantity of the population for each point out from the point location. The resulting surfaces around each point in a kernel density are based on a quartic formula with the highest value at the center of the surface, the point location, and tapering to 0 at the search radius distance. For each input cell, the total number of the accumulated intersections of the individual spread surfaces is calculated. Simply, you specify a neighborhood and the kernel just spreads it out from the center. Kernel density estimation incorporates attenuation at distance, whereas the other two are very sharp calculations that end abruptly at the edge of the neighborhood. Here, as a comparison, we have point density that shows rough borders between all these points. It's a point file being processed into point density, and in the same one we have a kernel density. The kernel density processes with a smooth tapered surface, and in general, in my experience, people have highly preferred kernel density for the fact that it's smoother and actually produces a nicer looking surface. Geoprocessing and analysis in action. When you have all these tools under control within your experience, stringing them together into a series of functions can be useful in order to create new spatial layers. One other method, stringing together geoprocessing tools, involves a function within ArcGIS called Model Builder. Model Builder is an application you use to create, edit, and manage geoprocessing models. In ArcGIS models, workflows that string together sequences of geoprocessing tools feed the output of one tool into another tool as input. Model Builder can also be thought of as a visual programming language for building workflows. While Model Builder is very useful for constructing and executing simple workflows, it also provides advanced methods for extending ArcGIS functionality by allowing you to create and share your models as tools. Model Builder can even be used to integrate ArcGIS with other applications. Additionally, Model Builder allows for repeatability, with less chance of making a mistake if you need to run the same tool multiple times. How Model Builder works. You end up dragging layers that you want to participate in the model, and by layers we mean similar to our chemical spill area or grassland files. Additionally, we can drag tools in, such as intersect, union, and merge, etc., into the model as well. Input layers are blue, and tools are in yellow. Output layers, tables, and objects are shown in green. With a little magic wand, you can connect the features using arrows, where you connect inputs with tools, and tool dialogues, similar to the ones that you've used in ArcMap in the open space, pop up. Order does matter in this section. Geoprocessing workflow. Let's give you a problem and see how we can break it down to solve it. So the problem we have here is find a suitable land to construct a power plant. We have listed criteria: suitable geology, low population, within 1 mile of existing road infrastructure, and a buffered zone to maintain around conservation areas. Within that, we would have required data sets. Based on criteria, we need geology, population density in a raster form, a road network, and our conservation area vector database file. From that, we can break our problem down into a geoprocessing workflow. We call our problem how to locate a series of plausible sites for a power plant. Remember that it has to fit these 4 criteria, and see how within this workflow, suitable geography, population density, roads, and conservation areas, we have broken down into tools. Within those tools, we have meta files that at the end of the day will be all combined down into our final product. So before we wrap up section 4 for lesson 11, I want to give you all an example video of stringing multiple geoprocessing tools together. So here we're going to run an example of how to string geoprocessing tools together. I've typed up a couple of sample questions. Number 1, we want to find the area of the chemical spill that coincides with the grassland habitat, which would be this area here, that we find the area and then calculate the area. And number 2, find the sample points with parts per million higher than 0.06 parts per million within 25 kilometers of our left, I'm calling this the left river, that also are in the grassland habitat. I want to make a point real quick. There are a couple of different ways to do this. The way I am doing it is just the method that I think would work. Just stick with me. We'll definitely get the answers out of this. So, number 1, find the area of the chemical spill that coincides with the grassland habitat. This is fairly straightforward. We need to find the area that overlaps between chemical spill and grassland. So in order to do that, we can just go ahead and run a quick intersect. Grab grassland and chemical spill. And always making sure it's going to the right folder. Let's say pollution intersect. And go ahead and run that. There we have our intersected grassland and chemical spill area. Pollution intersect, we can open the attribute table. And because it was an intersect, we have the attributes from both. Let's go ahead and do an area calculation where we can add field. We want to make this double precision, and we will call it area in km. I recommend when you are creating area or length files to always provide the units in the name. It's not always clear if you do not do that what units you are using to calculate the attribute field. So within area km, we've got a calculate geometry function. It'll automatically guess that you probably want area. This is a polygon. One thing to be careful of, again, is units. It'll default to square meters. We want to go ahead and let's say square K. And very quickly, we have 331,398 point whatever areas that are coincident between the chemical spill area and our grassland habitat. Go ahead and turn that off. Question 1, we have answered find area of chemical spill. We're good. So, number 2, find sample points with parts per million higher than 0.06 parts per million within 25 kilometers of our left river that also are in the grassland habitat. There are a couple of different ways to tackle this. First of all, we need to break the question down. Where are we looking? So, within 25 kilometers of our left river, if you were asking me, that's the first thing I would pick up on. So we want to pull information involving this river. So we go to our river file, and let's find out which one of these is the left river. Okay, so FID1 is the left river. One thing I want to point out, when you are running geoprocessing tools, if you have a file selected, it will go ahead and run it just on that selected file. So what I mean by that is when we run the buffer, because this is selected even though I selected it by hand, the buffer will only run on the file that I have selected. So we have buffer and we have our left river selected. Now the buffer is a tool that we are going to use to create our 25 kilometers away from the river. So input features, we've got rivers, and we're going to call this left riv buff. And units, we're going to go with kilometers and 25 kilometers. And again, it'll run just on this selected file. So if you run a spatial query or a non-spatial query in order to pull out certain information with the query and then run a geoprocessing tool on that, it will only run on the selected features that you've used to find with the query. So there we have our buffer. This is area within 25 kilometers of our left river. So let's go ahead and clear selection as usual. Now we're not so much interested in the river anymore as we are interested in the points that are within 25 kilometers of that area. So what we're going to do now, my preference is to run an intersect, keeping in mind, as always, that the intersect will produce the lower geometry. We're going to intersect our left river buffer with our all points file. And by lower geometry, what I mean is it will shoot out, because we are intersecting a two-dimensional object with a zero-dimensional object. It will shoot out the zero-dimensional object. Or between the river buffer and the points, what this intersect will produce are the points that are coincident between the buffer and the points. Let's call this buffer point intersect. Okay. And okay. So those are our, let's make them yellow, a little bit larger. Those are the points that are coincident along the 25 kilometer river buffer. So, what's the next step? Find sample points that are higher than 0.06 parts per million. We've got these points that are coincident with the 25K buffer. What we can do now is run a non-spatial query in the attribute table. Select by attributes, and we can do chem ppm, let's say greater than 0.06. Those are queried. Again, we haven't created a file. It's just saying, hey, these are the points that are within 25 kilometers of the river that have a chemical concentration higher than 0.06. So our query is complete, except now we need to create the standalone file. And we'll call this ppm 0.06 and save that. We want to go ahead and add that to the map. Let's turn this off and let's create our points. Let's make them a little bit larger. And then we have our points that have fairly high concentrations that are within 25K of our left river. And our final question is also within the grassland habitat. And like I've been saying, there's a number of different ways we could do this, but let's go ahead and try select by location this time. And we want to select from parts per million 0.06 that within our data grassland, and what is the operation? Show me the points, parts per million, 0.06, these reds, that are coincident with our grassland habitat. Go ahead and hit apply. Those are our points. Again, it is a query. Final operation, we'll go ahead and data export. And let's call this ppm 06, ppm 06 grasslands. And go ahead and set that up. And now we don't need ppm 0.06. So based on the questions given, we now have 2 answers. Let me make that bigger. We got our points that have a high concentration within 25 kilometers of our left river that are also in the grassland habitat. And we also have the area of the grassland that is coincident with our chemical spill area in units of kilometers. So in this video, we've strung together, let's see, select by attributes with the parts per million, select by location, the areas that intersect between grassland. We went ahead and took a look at if you select an area by hand or with a query, the geoprocessing tools will only run on the selection. And let's see what else. I think that's about it. Okay, let's say go ahead and as always, we'll go ahead and clear, and we have our 2 answers. That's it for stringing tools together.